basically you have an extra factor. You have a extra exponential factor here, and the method is the same whether a is positive or negative, except that whether you close it using the upper circle or the lower circle depends on the sign of a. So if a is greater than 0, then if you close it in the above, because C above has a imaginary part, positive imaginary part, and I times I is negative, then you have negative, positive A. That's the imaginary part of the that close up. A is negative, then you close it down. Okay, and then one more thing is the requirement for that is a little less restricted. So basically, you just instead of this, you can get rid of this C factor. You just require that the function f other than this exponential factor tends to 0. Okay, and that is one factor less, so you don't require that to go to 0 at least 1 over x, and it just goes to 0. Okay, so and the justification is also quite straightforward. The text will talk about that in more detail. So for this one, for assuming a greater than 0, you close it up, right? And so basically, you argue that f will go to 0. So you just assume you consider this path. This is theta. This is c theta. Or dc here is again is all it's from c into pi. Yes. And then you have f. And you have this e to the I a. This becomes c. Is all e to the I theta, which you can write as cosine theta. Okay, so that's this path along the big semicircle on the upper side. All right. Then again, you argue that it should be smaller than that. All the other things, the f. F you can argue that it's smaller than a certain number which tends to 0, like the text epsilon, because it will go to 0 anyway. And you have the R here. And all these are just phase. And then this cosine theta is also a phase, where e to the I a r cosine theta. This is a phase because cosine theta is real. So we can just ignore that. So it should be just the rest. This minus a r sine theta. Okay, this one. Right. Okay. Now the trouble seems to be that R is R goes to infinity, right? This big circle, R goes to infinity. But somehow you need to argue that this term will give you 1 over R. And the argument is that you look at this integral, the theta from 0 to I, and the argument, like the factor in the exponential function has sine theta, and the sine theta is from 0 to 1 at pi over 2, back to 0, symmetrically, right? Because that's sine theta. Right? And you see that it's symmetric between 0 to 2, pi over 2, and pi over 2 to pi. So you can restrict that to pi over 2 and multiply by 2. Okay, so just integrate from 0 to pi over 2 here. Right? And this function is a little bit difficult to integrate because it's sine theta. It's not that it's just a linear function of theta. But the argument is that you draw a straight line from 0 to, this is 1, 0 to 1. And I think it's this, there's a graph, and I think, and this line will be, you can figure that out. This is 1 and divided by 2 pi, I think. This is 2 theta, 2 theta over pi. Because theta is pi over 2, then you get to 1. So this is the line. And you can see that, you can show that this is less than sine theta over this range. They show that by some a little bit more algebra, but then graphically you can see that this straight line is less than the graph of sine theta. Is quite easy to see. So because this is sine theta is greater than this one, and if you substitute this into here, then you get a smaller argument for the exponential function, which is negative, so it decays less. This should be less than 2 epsilon into minus theta. Yes, factor some factor 2 or 2 over pi. And the reason going through all this trouble is that this integral, we know how to integrate. That just gives you e minus 2 and divided by whatever that is, minus 2a, right? And then evaluate that CO2, right? And whatever those are, this is just a finite number, right? That is nothing special. And the most important thing is divided by R, so you cancel this out, cancel R. And epsilon is a small number, goes to zero anyway, right? And the contribution from this big circle is 0, right? So that's maybe a simplified argument, but there's a name for this property. This is called the Jordan's lemma. Okay, and which is quite important in this kind of integral. So whenever you have this kind of integral, you cite the Jordan line, and then, as long as f is going to 0 at infinity, then you can say that the semicircle is 0. But it's only on one side. If a is greater than 0, then it's 0 along this upper circle, but not on the lower circle, because you change sign. You change sign, then obviously that on the other circle is exponentially large, then that doesn't work. But then if a is less than 0, then you can use the same argument and show that the lower circle will be zero, the upper circle will be not zero. Okay, so that you can do it that way. Okay, I think we can finish this example. I think there are two examples, but the first example is more straightforward. There's nothing subtle about that one. Let's do the second example. This is there. This is I is 0 to that's the integral. This is example 11. 8.5. Okay, and now when you look at the integral, obviously it looks like singular at 0, but it's nothing actually singular. It's what we call is removable singularity. That we talked about that before, because you can take a limit of the function at 0 and then show that the limit is 1. So we define this integral at 0 as 1, then you fix the singularity. Okay, and again, this is not from negative infinity to infinity. Then just like what we did over here, you fix that by just extend it to minus infinity to infinity. Because this is the odd function divided by odd function is even function. So you can do the same trick. Yeah, but yeah, you're right. Well, did I do it well? Oh yeah, that one is fine. All right. Now the other trouble is that this is not in the form. This is sine. This is not this is an exponential function, so we cannot directly use that. And the way to do it is just use what we did for the first type. Sine theta is 1/2i. You can do it like that. So sine x is 1/2i. And we have to do it. Actually, well, let's stay at real first, and then we'll because of this form, we can then go to the using Jordan line, right? Minus e to the minus. We could do that, and then we could use the Jordan line, you know. For first term, you get a is positive. So for this one, you can close it on the upper circle. For this one, you can close it on the lower circle. But then after you separate into two terms, now you get into trouble that this is now a true singularity. You don't have this removable singularity here, right? And it looks like you have trouble. How do you do it separately? And the argument is that because it's a removable singularity, so you can take out the 0 point. Let's just give some space over here. In mind the time. Okay, so for this allow x. So for this function, again, actually we'll later on going to see those x is along the real axis. Okay, now you take out a little bit of the integral delta and stop the integration and then resume the integration at the same delta after zero, after the singularity. Remember, this is a removal singularity, so the integral is finite. So taking out the small part doesn't matter as long as delta goes to 0, right? And the way of skipping that, doing something like that, you skip a distant delta before it and then resume after delta after it. It's called the principal value, or the textbook called Cauchy principal value, it doesn't matter. So to do that, but this doesn't matter, it's with removable singularity. And there's different notation. Some people like to use a principal value, PV. Some people like to use principal part or whatever. Some people just use a P, right, or principal part. And that either ways, all the different ways are fine, as long as you just define it properly, right? And the textbook like to use this a bar. This is basically taking out this. This is like the principal value. Is it okay? So is the idea okay for me? Skipping a little part, and this equal amount is important. So you skip the same distance before the singularity and after the singularity. That is important, right? And we'll use that fact in our calculation also. But it turns out to be important at least in some cases, right? And now you take out this one, and this is principal part. Now once you have the principal part, take it out of this integration at the singularity, then all these both terms are not singular anymore. Okay, both terms are defined as a path integral. This plus that, so this I1 plus I2 is this one, right? It's the whole thing. But now we need to do it one term at a time. And for the first one, so there's a 1 over 4I in front. So for e to the over x. Now this is positive a, so you close it up. So you can close it up. That's for the first term. And now this two part, and then this part not add up to a closed loop yet. So in order to form a closed loop, then you can close it either above it or below it. So you can connect another semicircle or radius delta, either going upper little semicircle or lower. Both will give you the same answer. Okay, so it doesn't matter. And then once you close the loop, you use the residue theorem. If you use the upper loop, then there's no pole inside. That will be 0. It means that this plus that plus this little circle is 0, right? Then the two straight lines add up to be the negative of this integral along this one, which is this integral from here to there. So that's fine. And if you use lower circle, then the whole thing whole loop contain one residue at the 0. So the whole thing is equals to 2 pi I times the residue of 0. But then you need to subtract the contribution from here to here because you add this little circle. Okay, you know what? And they turn out to be exactly the same. Right. So either way is fine. So if you close up, so that is so this integral will be 0 minus this. So this delta e to the d theta from 0 to pi. That's dc. You can change it to dc. This is dc, and then e to the I, z, I, z is delta, e to the I theta. That doesn't matter. Let delta goes to 0. And then this is delta e to the I theta. Right, x becomes g becomes e, delta e to the I theta. And delta cancels delta, e to the I theta cancels e to the I theta, and that delta goes to 0. This is 1. So, and integrate from 0 to pi. Okay, so that one will give you pi r, the first term with pi I. Right, and it's okay up to here. And now you can do the same thing for quite. The first one will be if you multiply divided by 4i, the first one will give you I divided by I and pi over 4. The first term will give you pi over 4. And you can obviously do the same thing for the second term, but close it in the lower part. But then now you realize that the second term actually is the imaginary part. It's at the complex conjugate of the first term because you have minus I. The second term is the same as the first term, right? So you can just multiply the result of the first term by 2 because it's just a complex number plus its complex conjugate is 2 of its real part. And the real part is pi over 4, so this is 2. Hopefully I can. Oh, yeah, I got it. So that's the final answer, pi over 2. Right? Do you know the final argument? So you can, I mean, if you want, you can just do the same thing for the second term. Now you close it down. You still have a pole on 0, and do the same thing, going up or going down, and then you figure out that the second term will give you exactly the same quantity as the first term. So you multiply by the first term by 2, then you get pi over 2. Is that okay?